given to us. So what's required is the diameter of the wire. So it's a very simple problem. We have a conductor, and we need to calculate this diameter to limit the maximum power here to 60 kilowatts. The formula you know for power consumed in resistance is P is equal to I squared R. And from here you can calculate the resistance of this wire. So it's equal to P divided by I squared. And we have the power, which is 60 kilowatt. That's single phase. So we are not writing here 3 or square root of 3. Divided by I squared, which is 100 ampere. And this will give us 6 ohm. And you know, this resistance has a formula we have taken in the lecture, that R is equal to rho L over R. I know we wrote that's RDC, but there's not much difference between RDC and RDC. At 50 Hertz or 60 Hertz, the difference is very small and can be neglected. If you want to be more precise, you have to multiply this by 1.02 as we mentioned, right? But we can neglect this. So this will equal to 6 ohm. So again, assuming here RDC equal to RAC. If you want to be more precise, you have to multiply this by 1.02 due to scale effects, as we mentioned. So you have everything here except the area, cross-sectional area. You can calculate it. So A will equal to rho, which is given 1.72 times 10 to the power minus 8 times L. L is given as 60 kilometer divided by 6. So this will give you the cross-sectional area of this wire. I have the calculation here. Will be 0.172 times 10 to the power minus 3 meters squared. And that's a circle. The cross-sectional area here is circle. This area can be written as pi r squared, right? Yeah. Radius square, or pi d squared over 4, the diameter, where d is the diameter. So from here you can calculate your diameter. So d will equal to 1.48 centimeters. This should be your minimum diameter, because you can still increase the diameter and your conductor will withstand 60 kilowatts. But if you decrease the diameter than this, there will be a problem, because you will not be able to limit your power at this range. So it's very simple and straightforward problem. Yeah? Any question? Problem number 2. If you look at this problem here, try to read it, please. That's a 60 Hertz single phase 2-wire overhead as solid cylindrical conductor. So it's 2 wire like this, say X and Y. And when we say solid conductor, it means each wire has made from just one conductor. We don't have bundles. So the X side here is one conductor, which has a solid conductor. We don't have bundle or stranded conductors. Same for line Y. Both have the same diameter, d equal 1.5 centimeter, and they are spaced by 0.5 meter. So what's required in this problem is the internal flux in each conductor. Anyone remembers the internal one? Last time when we tried to derive the formula for inductance, we got 2 components. One due to the internal magnetic field and one due to the external magnetic field. The internal one was constant. You remember it? Yes, L internal, and that will be in X or Y. As we mentioned, this will be constant, regardless the geometry or the dimension of your Y. Constant at 1/2 times 10 to the power minus 7 Henry per meter. If in the problem you are asked to convert it to millihenry per meter, you know what to do, right? So your answer will be always like this. In L will be always in Henry per meter. If you want to convert it to millihenry per kilometer, so half times 10 to the power minus 7. Henry is 1000, right? Millihenry. And meter is 10 to the power minus 3 kilometers, right? So it will be half times 10 to the power minus 7 times, when you put this in numerator, it will be 10 to the power 6 millihenry per kilometer. So it's 0.05 millihenry per kilometer. That's how to convert it. But remember always, your answer will be Henry per meter. Then you can transfer it to any other unit. Then you are asked to get the total inductance for each wire. Because we have the same radius here for each wire, Lx will equal to Ly. So Lx total will equal to Ly. And in here we have to combine both internal and external. If you remember from the lecture, we got a formula. Anyone remembers the formula? What's the formula here? Half times 10 to the power minus 7, 2 times 10 to the power minus 7, when geometrical mean distance over geometrical mean radius in general, right? So when we have two wires only made of solid conductors, geometrical mean distance is very easy, just the distance between centers. So in this configuration, geometrical mean distance is the distance between this center to this center here. So in single phase again arrangement, the geometrical mean distance can be calculated from the center of one conductor to the center of the other conductor. So GMD here is equal to 0.5 meters. Geometrical mean radius, I'm always writing here L because it's different between L and C. In L we have internal magnetic field. In C we don't have any internal charge. We don't have any internal static field for the conductor. It will be all on the surface. So because of the internal effect of magnetic flux, we have to compensate the physical radius. So it's equal to, we call it R dash, or physical radius multiplied by a factor, which from our derivation was e to the power minus a quarter like this. Or we can write it as 0.7788, right? R. So this will equal to, our radius here is 1, look at this, we have diameter, give it to us, right? So our radius, physical radius will be 1.5/2, that's R, multiplied by 0.7788. And this will be in centimeter, because the diameter is in centimeter. I didn't calculate the value because I calculated it several times. This value is in centimeter. Then you can calculate now L. So L will equal to 2 times 10 to the power minus 7 when geometrical mean distance is 0.5 divided by R dash. Please remember that 0.5 here is in meter. So you have to convert this into meter. Most of students in final exam forget to use the same units. So they use centimeter here and they use meter here. So when you get your answer here in centimeter, don't forget to divide it by 100. Make it same units in numerator and denominator. So when you do that, you will get L equal to 0.89 millihenry divided by kilometer. I converted it to millihenry per kilometer by multiplying it by 10 to the power 6 as I did before. And this inductance will be the same for X and same for Y. So it will be same for wire X and wire Y. If they are connected together, X and Y, so if you are asked to get L total, it will equal to Lx plus Ly, similar to resistances. So the total inductance for both wires connected in series will be Lx plus Ly. Sometimes we give you the problem like this, and we give you the diameter, and we give you also geometrical mean radius. Geometrical mean radius can be obtained from tables. So for this configuration, for example, I can give you GMR equal to any value. So if I give you GMR like this, I mean you have to use this value, because there will be a slight difference between your calculated value, GMR, calculated here from this formula, and GMR from tables. So in some problems, we give you GMR. And GMR here means the geometrical mean radius for one conductor. Especially when we have bundled conductors, and we don't want you to waste your time in calculating it, so we give it to you directly. So you can use it directly. You will find slight difference between your calculation if you use R dash, which is R multiplied by 0.7788. It will be slightly different than the value in the table, because this value, of course, is approximate. The formula is approximate. But in this problem, we don't have GMR. GMR is not given to us, so we have to calculate it using this one. This question number 2, is repeated in question number 8. So in number 8, we asked you to calculate the capacitance instead. So instead of inductance, you are asked to calculate the capacitance, C. The only difference in the calculation, GMD will be the same. So the geometrical mean distance will be the same. The difference here will be in geometrical mean radius. So if I just bring one dash from here. So in capacitance calculation, and that's number 8. For the same configuration, we are asked to calculate C. C is equal to 2 by F0 divided by length, geometrical mean distance, divided by geometrical mean radius, but here for C calculation, which is different than L. And you know F0 is 8.85, 10 to the power minus 12. And the result will be always in farad per meter. So geometrical mean distance here, GMD, is same. The distance between the two solid conductors centers. So it is 0.5. So GMD for L calculation is the same for C calculation. But geometrical mean radius here, we don't have any bundles. So this will be the physical radius R, which is 1.5 divided by 2. The diameter is 1.5. Without any compensation factor. We don't have to multiply it by 0.7788. So this will be 0.75 centimeters. So I will write here C equal to 2 by F0 8.85 times 10 to the power minus 12 divided by length, geometrical mean distance, which is 0.5 divided by 0.75. I forgot something? Yeah. Please always remember to convert them to the both units. Okay? That's in centimeter, so it has to be in meter like this. So they cancel each other. If you do that, you'll get as the number 8. You'll get C equal to 1.3 32 times 10 to the power minus 11. Your answer will be always in farad per meter. So if you want to convert it to nanofarad or microfarad per kilometer, you can do that. This capacitance is the capacitance from the line to ground, not between the two lines. You are asked also to calculate the admittance, which is y. Y is opposite to x. So y is equal 1 over xc. And you know xc, the capacitive reactance, is 1 over j omega c. So y, the opposite, would be j omega c. That's the admittance in series.
For the denominator, what's the
That's meter. This one is meter. Okay, j omega c, so it's equal to j. Omega is the angular frequency, 2 by f, and f in this problem is 60 hertz. And c, the value you got. And the unit here will be Siemens. You know that. It's opposite to ohm. Siemens per meter. So the answer will be J 4.9 times 10 to the power minus 6 Siemens per kilometer. I just converted it to kilometer. Any question? Okay. If you don't have any question, I assume you understand what I'm saying. Number 3, we have 3-phase problem now. 3-phase conductors, still solid conductors, so we don't have any bundles, and they are arranged in this equilateral triangle. Physically, we don't do that. Of course, we can't arrange them in this configuration. They can be either horizontally or vertically, but we don't care because they are transposed, as we mentioned before. They are fully transposed. So you are asked here to calculate the inductance and inductive reactance itself. So you have all the information to calculate this. Because the inductance for any phase, phase A, that's phase A, phase B, and phase C. And the distance here is 4 feet in each. So again, the formula, general formula for L, very easy to remember. L for any phase is equal to 2 times 10 to the power minus 7, then geometrical mean distance divided by geometrical mean radius. Always reminding you by that by this L. L means geometrical mean radius for L calculation is different than C. Geometrical mean distance here, because our 3 phases are at equal distances or space, so the geometrical mean distance is equal to, anyone remember the formula? The cubic root of the multiplication of the distance between each 2 phases. So it's the distance between phase A and B multiplied by distance between B and C, then distance between C and A. Again, for any arrangement, we can use the same formula. So if they are arranged in any other configuration, we can still use the same formula because they are fully transposed. And the distance here is measured from the center of each conductor. So even though we have this like not solid conductors, say you have the same problem, but instead of having one conductor, you have 4 conductors in each. So that's in phase A, and that's in phase B, and that's in phase C. So bundled like this, C and that's B. Your distances will be like this, from this center, here, this center, to this center of the four conductors. This center to this center, and this center to this center. So that's D, CA, DAB, and DBC. So you can always use this formula. Cubic root to calculate geometrical mean distance here for this configuration. It's cubic root of DAB, DBC, and DC. Measured from the centers of the conductors. All conductors now, because we have four conductors in each. Okay. So in this problem, we can calculate the geometrical mean distance, which is cubic root of 4 times 4 times 4, of course, will be 4. But if we have different distances, we can still use the same formula. Why? Because the lines will be always transposed. This should go here. Will be transposed like this. So we can assume that along the entire distance of the line, it will be at equal distances or equal spacing. Geometrical mean radius, because we are calculating L, so we have to use R dash, and we don't have any bundles. If we have bundles, we have another formula. If you remember, square root, you have to get M squared. We'll show it in another topic now. But for this one, it's just R dash, because it's solid conductor. So it's equal to R, and the diameter here is given in inch, 0.5 inch. So the radius is 0.25 inch. Anyone remembers the formula, the relation between inch and feet, to convert inch to feet? 12, right? So I have to divide this by 12, just to convert it to feet. It will be the same unit as this one. So I write it here, 1 inch equal to 1 over 12 feet. 1 inch is, sometimes we write it like this, and the feet were written like that. So the geometrical mean radius is equal to R multiplied by 0.7788, which is e to the power minus 1 over 2. If I'm calculating capacitance, I will not use this. And that's the only difference between calculating GMR for capacitance and GMR for inductance. Then you use your formula, L, to calculate it. So that's number 3. You will get 2 times 10 to the power minus 7, then 4 divided by, your R dash here will be 1.62 times 10 to the power minus 2. And both will be in feet. So equal to 1.1 times 10 to the power minus 6. And that's Henry per meter. Then if you want to calculate XL, the inductive reactance, it's only given 2 by F, which is 60, times L, 1.1 times 10 to the power minus 6. Will equal to 0.415 ohm per cloud. Just one comment here. Even though this one is given in feet and this one is in feet, your result still in Henry per meter. Okay, you know what? So this will cancel this. And what's controlling your unit here is mu naught, which is 4 pi times 10 to the power minus 7 Henry per meter. So our result will be always in Henry per meter. You understand this? Any question? You want me to repeat any problem? There was a suggestion that I go through one or two questions only during the tutorial instead of going through all questions so that you can understand. So as far as you are understanding, I will go to another problem. I will only stop when you have a problem and I can repeat it. Number four. Number four is just to train you on getting the geometrical mean radius for bundled conductors. So in this one we have 7 conductors. So we have one internal conductor surrounded by 6 outer conductors representing one wire. And we need to calculate geometrical mean radius for this one. So we have 6 outer conductors and one internal conductor will look like this. So the internal one is the red one. All of them are equal in the radius are equal to r. So that's the red one is the internal one, and you can see that it's surrounded by 1, 2, 3, 4, 5, 6 conductors. So we have 7 conductors here in one wire. So they are stranded together. And we need to calculate the geometrical mean radius. So just recall the formula from our lecture. Geometrical mean radius in general was like this. GMR is equal to, because we have 7, it will be 7 squared. Remember, it was n squared. N here is the number of bundles or number of conductors. So I have 7 conductors, so I should write here 7 squared. So that's the 49th root. Then I have to take one by one. So I have to write inside here 10 parameters multiplied by each other. So let us start by the internal one. Internal one has, first we start by the self one. Like I write like this. D, that's number 7. Okay? So I'll write it as D77. D77 here is actually R dash, just to make it symmetrical. Multiplied by D71, the distance between 7 and 1. Then D72, then D73, D74, D75, D76, and I already wrote D77. You finished the first conductor with all other conductors, then now you can move to another conductor. I'm still under the square. So this multiplied by. Then let us take one of the outer conductors. Let us take conductor number 1. Again, I have to write the self effect or self-inductance effect, which is D11. Again, D11 is R dash if I'm calculating inductance, or R, physical radius, if I'm calculating capacitance. So this formula is used for inductance and capacitance. The only difference is between R dash in L and R in capacitance. Then the distance between this conductor or subconductor and all other conductors. So D12, D13, D14, D15, D16, D17. You finish this conductor, move to another conductor, number 2, 3, 4, 5, 6, right? But you can notice that conductors, all outer conductors will have the same terms here, right? All outer conductors will lead to the same parameters inside. So I don't have to repeat it all the times. I can write 2 power 6 here. I will have to repeat it 6 times, because it will have the same distances. So you don't have to write it 6 times. So all 2 power 6. Then use your knowledge in mathematics and geometry to calculate these distances. I know you are better than me in calculating this, but let us just go through it. So now D77 and D11 representing R dash, which is R multiplied by e to the power minus 1 over 4. That's R e to the power minus 1 over 4. So all of these conductors are with the same radius R. Same radius R. Now, to look at D71. D71, what do you think about this distance? D71. 2R, right?
Yeah.
From here to here is R, from here to here is R. So D71 is equal to 2R. And this will be the same between 7 and 2, 7 and 3, 7 and 4, 7 and 5, and 7 and 6, is it? Is that right? So it's equal to D72, D73, D74, and D75. So you can now replace all of this by 2R. Is that clear? How about the other distances? From 1 to 2, for example.
Same.
D12. What's this distance?
Same. 2R.
Sorry again? Say 2R, right?
Yeah.
So if I want to write D12 is equal to 2R. And this will be the same distance between 1 and 6. So equal to D16. How about D13? This distance.
4.
Any idea?
4. 4R.
4R. Why 4R? It's not going through the center. It's tangent. It's coming here at this point here. But if you use geometry, if you connect this angle will be, and this one is R, and this one is 2R. So you can calculate this distance. So I'll draw it here. You want to calculate this distance. So what we have 2R here, and we have R. So this distance is equal to square root of 2R squared minus R squared, which will be a square root of 3 multiplied by R. And this distance is equal to this distance. Like this. Please look here because you'll be confused later on. This one is equal to this distance. So D13 is equal to 2 square root of 3 multiplied by R. And this will be the same between 1 and 5. Look at this. 1 here and 5. This distance. Right? Because you can just connect this point with the tangent here, and we will have the same geometry here. So this will equal to D15. D13, this one is easy and straightforward because that's the one you say. It's going through all the centers. So this one is 4R. So D14 is equal to 4R because that's R, 2R, and R. So 4R. So you got all the distances and you can substitute in this equation. You will get the answer. Your answer will be in terms of R. This will give us a geometrical mean radius of 2.18 R. So what this answer means? It means you can replace all of these 7 conductors, 7 bounded conductors with radius R of each by one conductor of radius 2.18 R, and it will give you the same performance. So all of this, it can be replaced by one conductor. Of course, the diameter here will be bigger, and this radius is 2.18 R. That's equivalent to this one. That's the meaning here. Okay. Number 5, we have again various configuration bundles, and we are asked to calculate the geometrical mean. So the first two ones, this one and this one, are straightforward, and I think you can do that. I'll just remind you by the formula. This one has 3, so geometrical mean radius is 3 squared, n squared. Then you take one conductor, conductor number 1, and write D11. Again, when I write D11, it means R dash. If I'm calculating inductance, or R if I'm calculating capacitance. Then D12, then D13, 1, 2, and 1, 3. And this will be repeated 3 times. So instead of repeating it, I'll write here cube. So one can write straight away, can write it as cubic root only, because this will cancel the square here. So cubic root only of D11, D12, D13. This one is R dash, this one is 2R, and this one is 2R. Straightforward. For this one, it's 4 conductors arranged in vertical configuration like this. And because there are 4, the geometrical mean radius will be 4 squared here. And the 2 outer conductors, this conductor number 1 and conductor number 4, will have the same parameters. So when I write here R dash, then this one to this one is R, 2R, sorry, and from 1 to 3 is 4R, and from 1 to 4 is 6R. Am I right? Right? Okay. That's 2R, 2R, 2R will be 6. So this will be squared. Why squared? Because conductor 1 and conductor 4 will have the same dimensions to other conductors. Then I can take the 2 inner conductor, will have the same dimensions or same spacing. So if I take this one, number 2, R dash, multiplied by the distance between this center and this center is 2R. This center and center of 3 is 2R.
Move the shit up, please.
Sorry. 2R. And the center of 2 and center 4 is 4R, right? 4R. And I can just square it. I don't have to go through 3 because 3 will have the same spacing. So that's how to do it. Easy, isn't it? The next one I will not spend much time in it, but I'll just show you this configuration, this one, because it's different than the circle group. This one. So what we expect here, we expect that these conductors in the corner, 1, 3, 7, and 9 will have the same spacing to other conductors. So I can write it to power 4, the corners. So let me just show you, you have here 9, so it will be 81 or 9 squared. And then if I start by 1, it will be R dash, D11, multiplied by 1, 2, let me assume that 2 is here. So to 2 is easy, that's 2R. And to 3, that's 4R. Same here to this conductor, which is number 4, 2R. To 5, this one. That's the problem here. How can I calculate this? Yes, I can. It's not tangent here. It's not similar to the other one. But if you connect this center to this center, you will have right angle here. And you know this one is 2R. This one is 2R. So you can calculate this distance. D15. So D15 will equal to square root of 2R squared plus 2R squared. So this will equal to square root of 8 multiplied by R. So that this one will be here. Then the distance between 1 and conductor 6, this conductor, same. If I connect this, the distance here is 4r and the distance here is 2r. So D16 is coming from this triangle again. You have 4r here and you have 2r here. So this distance is square root of 4r squared plus 16r squared. So it will be 20r. And so on. You can see that you can calculate the distances easily. So you have to repeat this with the distance here from 1 to 9. 1 to 9 is coming from this triangle, big triangle here. And from 1 to 8 and 1 to 7, we have done that. I'll just give you the final answer and you can practice this at home. So this will give you geometrical mean radius for this one is 2.6r. Any question? That's a single phase, and we don't have symmetry between line X and line Y. So line X has different configuration than line Y, and we are asked to calculate geometrical mean radius and geometrical mean distance. I'll stop until you finish talking. I'll stop. When you finish, just let me know. So please, if you have any question, ask me. For this configuration, we are asked to calculate geometrical mean radius and geometrical mean distance. The problem here in geometrical mean distance is we don't have symmetry between the two lines. I told you in the example I gave you, for 3 phase. If I have this arrangement, for example, if you remember it, when you calculate the geometrical mean distance, we can just take the center from this center to this center, this center to this center, and this center to this center, and then calculate it from the cubic root of the multiplication of the 3 distances. In this problem, geometrical mean distance can still be, it's single phase, it's not 3 phase, but it can still be calculated from the center of this line to the center of this line. And center here is this one, center is here, right? That's triangle. And the center here is this distance. But we have general formula for such unsymmetrical arrangement, and I will explain this in the next lecture. That is, if I have n conductor here and m conductor here, the geometrical mean distance can be calculated from this formula. N times m, and distance between dn1, conductor 1 in m side, and dn2 in m side, until the last conductor n and m. So what we have to do here again is to get these 3 conductors and apply this formula here. So I'll explain it in numbers. So we have 3 conductors in this side, in x side, and 3 conductors in m side, or y side. So it's 3 times 3. Then you fix one conductor here, say this conductor, conductor number 1 here, and multiply the distance of this conductor to all other conductors in the other side. What I mean here is this distance from here, from this center, to the center of the first conductor in the other side. And this distance can be calculated from the geometry given to you here. I have 10 centimeter here and 6 meter here. So the total distance would be 6.1 meter, right? Then this one is multiplied by, you have to finish this conductor with all other conductors in the other side. So multiplied by the distance between the same conductor and conductor number 2. Conductor number 2, again, I have 0.1 meter or 10 centimeter, then 6 meter,
6.2.
then, yeah, 6.2, right? 6.2. And then between this conductor and the third conductor, 6.3. Finished with this conductor, take the other one, which is this one here. So again, multiply the distance from the center of this conductor to all other conductors in the other side. So this one will be multiplied, the distance between this one and the first one, which is 6 meters. Multiplied by distance between this one and the second one, which is 6.1. Distance between this one and the third one, which will be 6.2. You finished with this conductor, take the third one, which is this one. And this might be a little bit common because you have to calculate it from triangles. So this distance, first, can be calculated from this triangle, which has a distance here. This one is 6 meter and 0.05 meter, half of 10. So 6.05. And this distance is calculated from this small triangle here. I calculated it and it's like 0.086 meter. Then you can calculate this distance. So this distance will be almost 6.05. Again, calculate the distance between this one and second one. From the big triangle, it will be around 6.15. And the distance between this one and the third one will be 6.25. What you will get here, you will get the answer is 6.15 meters, which actually is the almost the distance between the center of the conductors in Y side and this point here, because the distances here are very small. So if you don't want to spend time in this, you can approximate your solution and say that I will take the distance between the center of this side, which is easy here to identify. The center of this side is this center, right? That's the center. But the center of this side should be here in the middle, right? Given that the distance here is very small, just 10 centimeter, I can approximate this by this value, this point, which will be 6.1 feet, 1 5. So let me explain it here. The distance can be calculated from the formula I wrote, which is nm root of the multiplication of all distances between x side and y side, or because we have this here are arranged in triangular form, the center should be here. But the distance is 10 centimeter only. So I can say the center here is this point, which is 0.05 from this point, 0.05 meter. And the center here is definitely here at this point, which again is at 0.05. So 0.05 plus 6 plus 0.05 will give me 6.15. Is that right? 6.1. Ah, sorry, 6.1. You're right. 6 point.
No, sir, that's 0.1. 0.01. 10 centimeters, 0.01 meter.
Ah, this one is 1.
Yeah.
So 6.15 is right.
Yeah.
6, sorry, here. So 6.15 is right, which is the same result we calculated from the actual form with nm root. So in some discrete configurations like this configuration here, when we don't have any symmetry between x side and y side, we try to estimate the center of each side and calculate the distance between this center and this center. Otherwise, we have to follow it in this way. But you will get almost a slight difference between the actual geometrical mean distance calculated from here and the one calculated from this center to this center. So if you do that, you get the geometrical mean distance like this, and this value is again the same for C and L calculation. Geometrical mean radius, you have to get it for each side. So geometrical mean radius for x side, which is this side, I'll draw it here again. You have bundles, arrange it in this triangle, where the distance here is 10 centimeter. 10 centimeter. So geometrical mean radius is, we have 3 conductors, 1, 2, 3, so it's 3 squared. Then start with 1 conductor, we have to write r dash. Now it's not geometrical mean distance, geometrical mean radius. We have to write r dash if we are calculating L, or r if we are calculating capacitance. Multiplied by this distance, which is this center to this center, 0.1. This distance, which is 0.1 meter. Where r dash here is given to us. R dash for this problem, r is equal to 2 centimeter. So r dash is equal to 0.02 in meter multiplied by 0.7788. I have to repeat this for conductor number 2 and conductor number 3 will give me the same spacing, so I can write cube here, which can cancel the square. Then you will get your geometrical mean radius as 0.0628 meter. That's for x side. That's for x side, because in y side we have different configuration and we will get different geometrical mean radius. For y, y was like this, and the distance 0.1 meter. So geometrical mean radius here for y side is equal to, again, 3 conductors, so 3 squared. We start with r dash, then the distance, this distance 0.1, and this distance is 0.2. Multiplied by the inner one has distance 0.1 and 0.1. So we have to write it as r dash 0.1 times 0.1. The outer one here is similar to this one. So how about if I write square? Right? It will be the same. Where r dash again is given in this problem because we have the radius of x side, radius of y side. The radius is still 2 centimeters. So same radius. So you have r dash. This will give you a radius of 0.0628 for y. Sorry, for x, I just copied the geometrical mean radius for y. For x, the answer should be 0.0538. So what your answers here mean? Your answer mean that you can replace this configuration by just 2 conductors. In x side, the radius is 0.0538, and in y side, just 1 solid conductor. And in y side, the radius is 0.0628, and they are separated by a distance of your geometrical mean distance, which is 6.15. That's what your answer means. So if you have solid conductors in x and y side with such dimensions, will give you the same performance as the configuration we have started. That's the equivalence. Any question?
No, sir.
Okay. The last 2 problems we have in number 7. this configuration for 3-phase, and the line, the 3 lines are fully transposed. So this means the geometrical mean distance can be calculated from this formula. Cubic root, the distance between phase A and phase B. And when we say phase A and phase B, it means from the center of phase A to center of phase B, which is 6. From A to C, 6 plus 6 is 12. And from C to B, which is 6 again. So this will give you geometrical mean distance of 7.56 meters. What's given in the problem here is the radius for each conductor, and we have bundles. We have 2 conductors with each phase. So we have to calculate geometrical mean radius for this configuration. 2 conductors spaced by a distance of 30 centimeter or 0.3 meter, and the radius is 0.74 centimeter. So geometrical mean radius here for L calculation is equal to, because there are 2 conductors, so there are 2 square. First conductor, I'll write R dash, which is 0.74. Don't forget to convert it to meter. Multiplied by 0.7788. That's R dash.
Can you move it up?
That's R dash. Multiplied by the distance. And distance is 0.3. That's for the first conductor. Then you have to repeat it for the second conductor, or just write square here. So this will give you a geometrical mean radius of 0.0416 meter. Sometimes, as I said, we may give you the geometrical mean radius directly for such configuration. So if you see that in the problem, geometrical mean radius for this is given as 0.042, remember? So just take it and use it in the problem. You don't have to calculate it. This will lead to the value of inductance as 2 times 10 to the power minus 7. Then geometrical mean distance was 7.56 meter divided by geometrical mean radius, which is 0.0416 meter. So this will give us the value of L, 1.674. I converted it to millihenry per mile. You know the relationship between mile and kilometer, right? A mile is equal to 1.609 kilometer. And then you are asked to calculate XL. I'll write it for you. 1 mile is equal to 1.609 kilometers.
We're going to be expecting miles and feet and all that?
No, just for your information, because most of the codes and standards are from US, and they're using mile, feet, inch, so you have to also be aware of these units. But in the exam, it's just meter and centimeter. In number 8, in the last problem, number 9, yes, because we have solved 8. Number 9, the same problem, but you need to calculate the capacitance. So what will be the difference? It will be only in here, right? We don't have to multiply this by this value. So you will get your geometrical mean radius for capacitance, and use, of course, the formula for capacitance, 2 by epsilon naught divided by the GMD, same value, divided by the new G geometrical. Any question?
No.
Okay, thank you.